One of my very favorite things in science is that there's a certain power to it. So we can make what we want, or we can predict things that maybe haven't occurred yet if we understand the principles well enough. There's a certain power that science gives us in order to control the world or predict how the world will behave. And that's something that is awesome, in general. So when I have been going through the different factors that affect acidity of molecules, we can just memorize pKa's and know which things are more acidic than which other things. But what I think is often the challenge of, do we really understand things, and is this useful at all to us, is, are we able to predict the acidity of a compound we might be interested in, even though we've never encountered it before. So aniline, C6H5NH2, would be a good target molecule for me to think about, because up until now you may not have even known that this exists. And as I draw out the structure, hopefully the structure of this is similar to the structure of some molecules that we have studied. So when I see aniline, then I can compare that, because it's got a phenyl ring in it, to the only other compound I know of with a phenyl ring in it. Based on what I've covered in this class anyway, I know quite a few compounds with phenyl rings in it. But one of the compounds we studied in great detail is phenol, which hopefully you see the similarities between phenol and aniline in that they both contain the phenyl ring. Right, so if we know the acidity of this guy, and we do, it's pK equals 10. That's one of the compounds that I'd say is simple and straightforward and worth knowing, that an OH group attached to a phenyl ring, a phenol, is going to have a pK somewhere in the neighborhood of 10, depending on other factors like whether there's fluorines out here in the ring or something else attached to the ring, something like that. But pK of 10 for this one is a good starting point to try to compare to this one. And then I notice that this is an OH and this is an NH. So again, how do OH groups and their acidity compare to NH groups? So that's where I might compare water, right? Water is pK equal 16 to ammonia. Right, so in this case I have an OH group just attached to hydrogens. Here I have an NH group just attached to hydrogens. And if we change the oxygen attached to hydrogen to a nitrogen attached to hydrogen, that has a dramatic effect on the pKa. So as we studied these two, we noticed that there's an electronegativity difference between oxygen and nitrogen. Those both being group 2 are similar in size, so electronegativity is the force or the property of the atom directly attached to hydrogen that's going to affect its acidity. And if we memorize that water pK is 16, ammonia pK is about 35, then we can see that changing from an oxygen to a nitrogen, you would expect making that change in electronegativity would add about 19 pK units, right? So then, likewise, if you were to add 19 pK units to 10, you would get a predicted pK of about 29. So that's where, again, looking at a factor that affects the acidity and changing just that factor in our molecule should have a similar effect. The other thing that we're doing here is, if we look this way, right, going from water to phenol, that's a comparison we made before. We're adding in the phenyl ring reduces pK by about 6 units. So hopefully adding in a phenol group going from ammonia to aniline should have the same effect of -6, and if we do 35 minus 6, we again get 29. So we're predicting the acidity of aniline to be hopefully pK equals 29, by either looking at the effect of a phenyl ring being attached to the atom attached to hydrogen, which should drop the pK by about 6 units. Right, that's what we saw going from water to phenol. And so 6 units less than 35 is 29. The other thing that we can do is from a reference compound phenol, going from an oxygen attached to hydrogen to a nitrogen attached to hydrogen should increase the pK by about 19 units. So 10 plus 19 is 29. So using either prediction, changing the resonance or adding in resonance by adding in a phenyl group should increase the acidity by about 6 units. And then looking at electronegativity, going from an oxygen to a nitrogen should decrease the acidity by about 19 pK units based on the electronegativity of the atom directly attached to hydrogen. And that would also predict 10 plus 19 is 29, 35 minus 6 is 29. Using either factor to predict, I think the pK of aniline is really 27, so we don't get an exact answer, or we don't model reality exactly by doing these types of predictions, but that's a pretty darn good estimate. If the real pK is 27, we're predicting 29, which is pretty good. Now, one of the problems you'll see if you try to look the pK of aniline up in the literature is, since this is a base, right? Aniline is a base. The nitrogen with the lone pair is going to accept a proton more readily. If you try to look up the acidity of aniline, what they're going to give you is anilinium chloride. So pKs are generally attached to acids. So the free base form, right, aniline is a base with a pK of about 29, 27 to 29 you might say. But if you add HCl, and this is what a lot of drug companies do all the time, is you have a basic form of the drug, and then you have an acidic form of the drug, and they'll generally give you the pKa of the conjugate acid. So anilinium, the pK is going to be somewhere in the neighborhood of 10. Again, what I should do is get out a reference and look up the pKa and I get the pK of the anilinium ion is about 4.6. And the reason I was saying it was about 10 is because I know ammonium is about 10. But because of the resonance here, again I would predict that 10 is a reasonable reference because NH3+, adding in the phenyl group should drop it by about 6 units, just like we just saw. So the pK of aniline is 10 minus 6, or about 4. If we look up the value, it's 4.6. So anilinium, being positively charged, is more acidic than the neutral aniline by quite a bit. Charge effects are very significant. Anilinium pK is 4.6. Aniline pK is about 29. Sometimes if you look up the pK of aniline, they're going to report the pKa of the conjugate acid instead, which I think is misleading and incorrect, but that's just the way the literature often does it. So there we go. We have a predict the acidity of a compound we've never seen before, and we did it fairly successfully by considering either electronegativity or resonance or both. And I like to set up a little square of 4 molecules where we're changing things in similar ways along both axes of the square. So from either phenol to aniline, we're changing the atom directly attached to hydrogen, just like in water to ammonia. And then from ammonia to aniline, or water to phenol, we're just throwing in the phenyl group. So by doing the sort of control versus experiment, controlling one thing at a time, we can see the effect of that one change. So the one change of electronegativity difference or the one change of the resonance difference should have predictable effects on the acidity if in fact all the stuff I've been telling you is true. And it looks like it's working out pretty nicely.